All right. Well, after a long hiatus, we are back with another episode of Author Meets Physics, which is the YouTube show for philosophers of physics by philosophers of physics. Uh, Today, my guest is Doreen Fraser of the University of Waterloo. Um, and we're going to be talking. So, on previous kind of episodes, I've been focusing on work that excited me by uh like junior scholars, and I feel like now is a decent time to kind of branch out and look at stuff that I consider to be kind of classic work. And so we're going to be looking at Doreen's paper, The Fate of Particles in Quantum Field Theories with Interactions, which is probably a good I meant to kind of check this, but I didn't. But it's probably a good candidate for like the paper that I've cited the most over the years,
That's
maybe.
nice to know.
No, yeah, because like the stuff that you do in this paper is relevant to all sorts of stuff. And it's pretty uh it's a pretty definitive work in a way. So that's kind of a yeah. Anyway, I consider it like one of the classics of philosophy of physics that has been written within the span of my career. Um, and because this paper is a classic, Doreen also has a new paper, which is kind of a follow-up on it, a review article on particles in quantum field theories. So we'll be kind of moving on to talking about that at some point in this discussion too. So yeah, like let's talk about the essay. So maybe we can kind of start with a bit of like it usually works best maybe if I kind of like give my impressions of like the kind of like 10,000 feet big picture thing that's going on in the essay, and then like you'll probably have some things to correct some of what I've said, and so then we'll kind of get started there, and we can get the idea on the table. And
That sounds
yeah.
good. I think, as you said, like historical context, it feels like this was a long time ago. So
Yeah,
starting
so
off
true.
with not only like the 10,000 feet view, but well, it's not quite 10,000 years ago, but that kind of historical view almost as well.
Yeah, yeah. I mean, okay, so rewind the clock to Dave's in grad school. Um, and
And me too, actually.
yeah, that's right. Was this your job market writing sample paper?
Yes. Yes, it was a chapter of my dissertation.
Right. That's right.
Yeah.
Um, okay, so so here's kind of the conclusion of the paper is, at least there's no hope for a view on which particles are part of the kind of basic ontology of quantum field theory if we include interactions. Um, and you kind of proceed in like a kind of like set them up and knock them down fashion, in the sense that, oh, here's a bunch of ways that you might think you could do this. That is to say that you could like do the thing that you can do in free linear quantum field theories, where you can say, okay, well, at least I've got a Fock space version of the theory that has a number operator. And so there's some observables in the theory that have a kind of interpretation as describing, particle properties, right? Um, but uh, uh, you know, there's a variety of reasons why this isn't going to work in interacting field theories, in your view. So, first idea, which is the thing that a textbook would tell you to do, is to uh, look to the Fock space for the free theory as a space that could be used, different superpositions of those states could be used to talk about the interacting theory. But no, Hogg's theorem tells us that interacting states cannot be superpositions of free states. They can't live in the same Hilbert space, and so that's a no-go. And then you go through some candidate ways to try to uh, take an interacting theory and do to it the same thing that you do to the free theory when you construct a Fock space. And you say, oh, well, there's some reasons why this can't work. either it ends up not being relativistically invariant, or there are properties that these supposed interacting Fock spaces have that are pathological and make it look like they're not really talking about particles. So that's kind of, I take that to be kind of like the 10,000 feet argumentative structure of the paper. So
yeah. So that's roughly, so that's roughly right. So when I wrote this paper, I saw it as contributing to a growing literature on why there can't be a fundamental particle interpretation of QFT, as you said. So the conclusion wasn't surprising of the paper, but it was thinking about interactions that was the original part of the paper. So one of the things that thinking about interactions allows you to do is come up with a set of arguments against particles that doesn't hinge, for example, on questions about localizability, right? So the sort of David Malamud's arguments and other related precisifications of those arguments for why you can't interpret free quantum field theories in terms of particles hinged on problems to do with localizing the particles. But you don't even have to think about that when you move to interactions, because there's even sort of more, because as you say, you don't have the Fock space representation available. And that was doing a lot of the formal setup work that then had a fairly like straightforward interpretation in terms of at least something that was countable and at least particle-like in that respect. So that's the thing that you don't have anymore when you move to interactions. So yeah, so there's like three parts to this. The first part is ruling out just using the free Fock representation to represent interactions. And that's where Hogg's theorem comes in. And so that was the other work that I did with John Ehrman, and in my thesis was more about that. As you say, the basic problem there is that you can show that when you try to represent the interacting system, including the Hamiltonian and all the sorts of things you'd want to represent on that Hilbert space for the free Fock representation, then nothing's well defined anymore, right? So that is a problem if you want to use the Fock representation to underwrite a particle interpretation, because then you don't have a no particle state that has the properties you want. You don't have a one particle state that has the properties you want. So the whole thing just really falls apart, right? So that's the first step.
yeah, great. So that's kind of like, I appreciate you foregrounding one of the things that is really striking about what you show, which is you don't even have to have an especially high standard for what counts as like having particles in the theory in order for it to be in order for actions to be or interactions rather to be a problem for that, right? All you need is to say, well, there's got to be countable entities with a discrete number of them in some sense. And already that kind of very weak particle interpretation of a quantum field theory is gonna fail in the case of interacting theory.
Yeah.
So
So
yeah.
so let me fill in the in some sense, right? It's not the localizability that turns out to be important. It's the fact that you hope the no particle state is going to be like the lowest energy state, right? You hope that, and then the one particle states are really what convinces you that you have a particle interpretation, because they have the right energies that particles should have in relativistic theories. So I think that's really the key, like basic piece that allows you to interpret the Fock interpretation in terms of the things you're counting are particle-like in that respect.
Yeah.
You would expect of a relativistic theory, right? So
yeah, that's great. So that actually gets to one of the things that I have started wondering about this kind of argument, which so what I'm about to say isn't original to me. Noel Swanson kind of pointed out to me a couple years ago, and he's off and on he's kind of talked about writing something up about this, but he's had other things that have taken up his time. But so like one of the things, so any kind of like no go argument, like the ones that you're talking about, is essentially it's gonna say, well, like the thing you want to do is a no go in the sense that if you try to do it, you're going to end up saying some things that look absurd or saying some things that look like kind of like unacceptable consequences or something. And so like as you point out, right, one of the things that we're assuming is unacceptable here is the idea that the vacuum or lowest energy state might not coincide with the zero particle state, right? But like it's not, I mean, like, I almost wonder, like, does it have to be analytic to the idea of a particle that putting more particles into the universe has to raise the energy, right? Because it's like you could imagine kind of laws that things, things might be set up. And again, this is a point due to Noel. This is not a point due to me. But you could imagine a situation where like laws might be set up so that there's some kind of sweet spot number of particles where like, if you take particles out and reduce things, the number of particles below that number, then you're like adding energy. Like it's kind of like the universe has kind of like a sweet spot number of particles that it wants to contain. And if you go above that amount, the energy goes up. But if you go below that amount, the energy goes up. It's a weird conception, but like, like it's widely understood that things get weird in quantum field theory. And one of the things like, so like, folks talk all the time about kind of like the vacuum containing a sea of virtual particles or something like that. Like you kind of wonder, like, is that what could be going on here? That like really there's like a vacuum with a sea of maybe infinitely many virtual particles, and so like that means that the vacuum state isn't the zero particle state anymore.
Yeah. So I mean, I think if you just had the arguments about the zero particle state, then you might wonder whether there's something you could do, right? But you also have arguments about the one particle states. This is kind of why I think the one particle states are important to the free Fock representation, and why we think of that as being why we think of the number operator as counting particles and not just energies, right? Because they have the right energies per particles. But you might think, okay, well, before you look at any of the analysis in this paper, it's not so surprising if you introduce interactions that say the n particle states might not have energies that line up with n non-interacting particle states, right? I think this is what you're suggesting. But I think this is one of the interesting things about going through and pursuing like trying to set up the Fock space for the interacting case, is that you realize that actually the problems come in before you get to n particles. 0 and 1 particle cases are already problematic, right? So you can, if you're thinking about adding more particles and if there's interactions, then that might be doing funny things to the total amount of energy you have. But this is problematic before you even get to that point, right?
And now there's a couple of things, there's a couple of forms of that problematicity could take. Like, is it that the difference between the zero particle state and the one particle state isn't the sort of difference that you would expect to be there between a zero particle state and a one particle state? So the problem is about the relation between those two states. Is that kind of?
Well, and so I think this depends on what kind of so there's 3 different ways you can go, and I'm arguing that none of them work, right? So we're talking about the first option right now, which is to just go ahead and use your free Fock representation. And then I've said, look, you've said, look, none of the operators that you want, the energy is not going to be well defined, for example, on that Hilbert space representation if you have an interacting Hamiltonian. So this is why you're getting infinities, right? So then one thing you can say at that point is, okay, well, no kidding, then we need to renormalize, right? And so that can be one way to try and then this is what can lead you to think about the vacuum as being not a state of nothing, but a state where there's like infinitely many different things going on at once, right? So but then I would come back to the same point that you don't have the same reassurance that what you're counting are actually particles in the nice way that you do in the free case.
Yeah. I mean, so in terms of like how hopeless are the three options, it definitely seems like option one, just use the free definition of particles, is like the most hopeless, right? Like it just
Yeah.
it seems
Well,
disastrous.
it depends on your
Okay, go
perspective,
ahead.
right? Okay,
Yeah.
yeah, I agree with you. But anyway, I think that this is a place where um uh there's like there's disagreement in philosophy of QFT, which is a much richer place now. I think it's fair to say there's a lot more going on. There's a lot more people studying philosophy of QFT than there was when I wrote this paper, which is great. So there's people have different points of view on that question, right? Of like what you make of it at that point. Do you say, okay, well, then unless you can construct a model for a nice mathematically rigorous model of the standard model that satisfies some set of your axioms, then I'm not interested. I'm just going to keep trying to work with this with the textbook version of the theory, and then and that's one way of going, right?
Yeah,
But
right.
I think I'm taking us off in a different direction. I do want to talk about the other two options. So maybe that's the
Oh,
best
for
thing to talk
sure.
about
Well,
next.
so I do too, but
Yeah.
I mean, like, let's so I think it's worth dwelling on the Hogg's theorem stuff
Yeah. Okay.
for a bit, because I think that is, like, when I think of your dissertation work, that's one of the kind of the things that was uh I mean, a pretty special achievement of it was like getting a good look at Hogg's theorem for the first time in a work of philosophy. But like um so okay, so one question of the kind of like the kind of like what's the present day dialectic and how does that differ from the time when the paper was wrote, which was definitely a time when like a much bigger fraction of the work on quantum field theory was kind of taking an axiomatic approach, like the one that you or I tend to take. Um, so like, do you think though that there are folks around now who would say that like there's really nothing wrong with taking an interacting theory and um treating it as if the observables from the free theory apply to it, and taking that literally as kind of like, I mean, so somebody like Wallace, I take it what he would say, as you kind of point out in the review article, which we'll get to, but like the kind of thing that I take it that Wallace would say as well, there are domains in which the free theory is a good approximation to the interacting theory. And so like, when you're dealing with a state that is well approximated in some sense by free theory states, then it's okay to kind of like think of this as a state that in a non-fundamental sense has
Yeah.
particles, right? A state that kind of like, as he would put it, has like emergent particles or something. But like, but I take it he wouldn't say that it's a good idea to look at the observables for the free theory and say, these give me the right degrees of freedom to use to talk about the interacting theory, right? Like, is there, do you think there's somebody who would say something like that?
Um, no, but I think that maybe those 2 points of view are closer than you think, right? So I think
Okay. Okay.
everybody would probably agree that, look, particles are not part of our fundamental ontology when we use
Yeah.
quantum field theory, right? So then that's a negative statement. Then there's going to be lots of disagreement about how you make out what the positive role of particles is, right? And so yeah, as you just said, I think that using the free Fock representation would be one way to explain. Well, there's many different ways to use the free Fock representation to explain how the particle concept can play a non-fundamental role, right? So,
Yeah.
but I think what you were suggesting, though, of wondering how worried we should be. So one way of taking those kinds of concerns about how worried should we be if we have a vacuum state that stays not the ground state, and maybe even interactions are going to reduce the total energy of the of the system, right? If depending on what kind of interactions you have. I think those if you think about the kind of like the kind of cartoon picture of the vacuum as being a place where lots of things happen, that's something that comes about from having to renormalize often, right? So that's the sense in which I think those two pictures can kind of not reinforce each other, but there might not be as much difference between those two ways of thinking about things.
Yeah, good. Yeah, and something we should probably also flag for the kind of listeners is like the question of whether renormalization can really get around the premises of Hogg's theorem in a kind of like way that that's unproblematic, right? So maybe do you have things you'd like to say about that?
Yeah, sure. So yeah, so the argument I make at the end of the first part of the paper is arguing that Hogg's theorem shows that you just can't, that what you need to have well defined is not well defined for the interacting system in terms of the free Fock representation. So then you can't get your argument that your vacuum state is the no particle state, or your argument that the one particle states are the one particle states off the ground, right, in that representation. So then in response to that, a natural mathematical move is to renormalize. So then instead of having infinite energies, you'd have the right energies that you would want. So one way of thinking about it is in terms of Hogg's theorem. If you look at the assumptions that go into there's different versions of Hogg's theorem, but if you look at the assumptions, one of the assumptions is that there's some time at which the free Fock representation of the free vacuum representation is unitarily equivalent to the representation for your interacting system, right? So so that's an assumption that's you can show is not the only option, right? Because because of the Stone von Neumann theorem, right, which fails in the case of a infinite number of degrees of freedom, a field theory context. So then you have mathematical reasons for thinking, okay, you can assume that, but that could turn out that's like not a trivial assumption anymore, right? Because there's continuously many alternative unitarily inequivalent representations of the canonical kind mutation relations that you could use, right? So so one way of thinking about renormalization would be to say, no, you're going to stick with that assumption that you're going to keep the free Fock representation, and instead one thing you can do is introduce cutoffs or some type of regularization procedure whereby you then have a finite number of degrees of freedom, and then everything is unitary again, right? So that would be one way to try to save that assumption that's key to Hogg's theorem.
Yeah, and so I mean, let me know if you kind of agree with me about the lay of the land here. But the thing that's always seemed to be the case to me is, in order to really get around Hogg's theorem by doing that, you'd have to have both ultraviolet and infrared cutoffs, or that is to say, like regulators that get rid of both UV and IR infinities. And like while it's physically plausible that UV cutoffs are something that kind of like, at least we can say, oh, we have good grounds for supposing that quantum field theory isn't going to do a very good job of describing the real degrees of freedom in the ultraviolet. It just seems to me to be kind of not similarly well motivated to suppose that it's got to break down at long distances, right? I don't know if that's kind of like,
Well, okay, I think of Hogg's theorem as being the kind of first indication that interactions are going to lead to are going to undermine certain standard assumptions you find in textbook QFT, right? So I think the first one that has to go is the assumption that you can represent interactions using a representation that's unitarily equivalent to the free one, right? But then you're also going to have to smear in space and time. And so there's a whole bunch of other things I think you're going to have to do once you start constructing or trying to construct actual interacting models. Um, so the thing about Hogg's theorem is, in fact, it holds for two free systems. So you don't even need to get to interactions, right? So you're going to be able to show that if you have two free systems with different masses, you're going to need to use unitarily inequivalent Fox-based representations for those as well, right? So you don't even have to get to interactions, but you do in the case of 542, so 5-4 scalar self-interactions into space-time dimensions, that's been constructed, and you have a representation that's unitarily inequivalent to the free Fock representation in that case. And all you have in that case is IR divergences. So there's a sense in which, and Hogg's theorem applies, right? So there's a sense in which Hogg's theorem is really only telling you that even just due to IR divergences, right, you're going to need to move to a different unitarily inequivalent representation. Now, I say, like, from a mathematical point of view, if you're thinking about how the mathematical formalism of Hilbert spaces or algebraic formulation is used to represent quantum field theoretic systems, relativistic quantum systems, then it seems natural to realize that, okay, yes, that assumption that was natural in non-relativistic quantum mechanics, that all the physically relevant representations, unless you have really weird systems, are going to turn out to be unitarily equivalent. There's no reason to expect that mathematically to apply anymore in the context of field theory, right? So, but you could resist that, right? And so the way to resist that is to introduce the IR and UV cutoffs. Then you get into a finite number of degrees of freedom. Then you're back into ordinary kind of quantum mechanical kind of context. You still have to renormalize. It's just that it's finite, right? So there's the other part of it as well. So you're still going to have to interpret renormalization, but it's going to be finite instead of infinite in that case. So your question was about how you would physically justify the cutoffs. I think that that's a kind of question that would come along, like, so that would be a way you would try to justify that move. To me, exactly. that gets things backwards, because I think that there's still questions about how to properly set up quantum field theory, or relativistic quantum theory, if you want to put it that way, in a mathematical way. So so I just gave you my argument that I think it makes sense to give up on that assumption that everything's unitarily equivalent in the first place. I think really, you asked about the UV. I think our best evidence from that's going to come from quantum gravity. I think those considerations are not really good. I mean, there's a question about what the world is actually like, and then there's a question about what you're representing when you're representing things using quantum field theory. So I think you could look maybe for extrinsic justification for those cutoffs to get yourself out of this calculational problem, but that seems to me to be a kind of backwards way to approach quantum field theory.
Yeah. So this gets to one of the kind of methodological sort
debates,
of,
you put it that way.
Yeah.
Yeah.
Well, and one of the points of view that you bring to the table, right, which is you're kind of interested in the question of like, we might say, like, interpreting quantum field theory sort of like by itself, or, you know, in a way kind of like on its own sort of like on its own terms, rather than as a theory that we are constantly keeping in mind to be only an effective theory that limits to some unknown better theory or something like that, which is more the approach that I guess, as you were saying, right, has kind of come to appear, more and more in the literature the last few years.
Yeah, so maybe let me say a little bit more about how I think about quantum field theory. So I should say I've actually written about effective field theories as well. So it's not like the question is whether you obviously effective field theory techniques as a set of applied mathematical techniques have been really useful in all sorts of areas of physics, and are important. I'm really, I was just telling you, I'm teaching a seminar on philosophy of applied math this term. So I have always been interested in questions about applied math and how we use math in physics. So I think there's all sorts of interesting conceptual questions to do with effective field theories, and it really there's still, I think, a lot of interesting questions for philosophers of physics to look at there. In terms of thinking about this question we started with of, okay, we have quantum field theory. What is the fundamental ontology of quantum field theory, if we can make sense of that? So the claim of the paper was it's not particles, right? So in setting up that question, the way I was thinking about quantum field theory is I was, as you said, taking it on its own terms, taking it seriously as representing the world as being a particular type of way. Then I think you can recognize after that, okay, this is a description that you get from quantum field theory, which is not going to match the actual world, right? The possible world in which quantum field theory is true is we don't think our world, right? Because it doesn't incorporate gravity yet, among other reasons. I think those 2 points of view are consistent. It's just a different way of setting up methodologically or philosophically what the interpretive question you're asking is. I also should maybe say a little bit more about points that I think maybe should get more emphasis in thinking about quantum field theory and how it fits into other theories in physics. One of the things that strikes me thinking about quantum field theory is it's a theory that's still undergoing development, right? So I like to take a historical point of view on the field, and there's been a lot of actually excellent historical work on the history of QFT that's been done recently, but you can see how the formalism develops from perturbative renormalization methods to renormalization group methods. There's all sorts of developments that happen. There's developments in axiomatic techniques and construction techniques. There's a lot of work that's gone in to try and more to figure out what the proper mathematical formulation of the fundamental physical assumptions of relativity theory are that go with the fundamental assumptions of quantum theory. So I think if you think about say, my favorite example is thinking about classical physics, right? Think about post-Newton. The Principia is not something that you would recognize from the point of view of what it is that undergraduates right now would learn classical physics is about, right? There's several centuries of developments that had to happen, physical input and mathematical developments that had to happen to get to Lagrangians and Hamiltonians and analytical mechanics, right? So it seems to me reasonable to think, okay, the first idea we had about how to formulate quantum field theory mathematically, which worked for quantum electrodynamics, why would we think that's the final word on what the right mathematical framework is?
Good. Yeah. Yeah. Of course, that all sounds right. I mean, so
Thanks, Dave.
so when it so the upshot then is that there's a kind of like provisional or tentative attitude that we should take towards the axioms that present day axiomatic QFTs start from. Is that kind of the
Well, in one sense, in one sense, yes, and in one sense, no, right? So this was all started when you wonder about constructing models of the axioms, right? So so I think another important point to note is that the axiomatic approaches to QFT started by looking at the standard mainstream versions of the assumptions that were made, right? And then tried to put them in mathematical, well, investigated their mathematical properties, found due to problems like Hogg's theorem, the assumptions as they were first written down didn't fit together mathematically, so then revised the assumptions, right? So I think it's important to remember that these are not like axiomatic QFT doesn't get its axioms from some distant like
axioms aren't coming
it's not
from
like
a
they come down from
priori
God.
thought.
It's like they come from like, I mean, it's a similar starting point. It's part of this kind of well, I see it as being part of this sort of like cleaning up project of trying to figure out what the right mathematical framework is. So yes, I mean, as we keep going on with this project, I mean, there's like within algebraic QFT, there's been different proposals for what the axioms are as well, right? So that it's not like there's this settled idea of what in algebraic QFT the axioms are, right? They're all related, but there's different choices you can make.
Yeah, yeah. I mean, now one question then is, how open should we be to um like potentially rethinking the axioms in a way that's kind of like, instead of trying to clean up, so here's an attitude you might take. Instead of trying to clean up quantum field theory understood on its own terms, what we should do is instead think of things in a Wilsonian way, that is like everything is an effective field theory, everything has its domain and can be expected to kind of like break down outside of that domain. And so the right direction to take things would be to, on this point of view, try to clean up that approach rather than trying to clean up an approach in which quantum field theory is treated as like not in the real world, but as for present purposes, kind of like a complete theory or something like that, right? That is to say, like the way that the algebraic approach is mostly proceeded is by saying like, well, let's take quantum field theory as kind of like as its own thing and clean it up kind of on its own terms. And one might say, well, no, the way you should do it is treat it as an effective theory and clean it up on those terms. That is, like, make it a well-behaved effective theory rather than a well-behaved theory that that doesn't break down in certain domains.
Yeah. So I don't, so are you thinking about I think the lines might blur at a certain point, but I think one of the reasons why it's important to, in some respects, push quantum field theory to its breaking point is obviously we don't have a good candidate for quantum gravity yet, right? So I say that with all due respect to people who've made different proposals, but it seemed like there could still be ideas that we're missing, right? And so what kinds of ideas are we missing? Who knows? But like, it could be that we're missing some subtle points about how you even put special relativity together with quantum theory. Those could be physical points. They could also be mathematical points, right? I think one of the things that you're closing off when you decide at the beginning, okay, we're going to stick to the free Fock representation, and that's really like all we're going to need to do physics, because we're just going to like put in cutoffs when we need to and do whatever, right? I think what you're missing is that the continuously many unitarily inequivalent representations that you get in field theories are a representational resource, right? So they allow you to represent things that, and this is a point that Laura Ritchie's made in various ways, but it's a resource that you can use to represent different aspects of the world that if you just stick to your one Hilbert space, you're not going to be you're not going to have open to you. So I think there's like two kinds of things we could be missing. One is broadening up the mathematical framework might help us to see that things that seem like they're inconsistent or incompatible can actually be put on the same footing if we just have a broader mathematical framework in some way. It could be that there's some physics we're missing. I don't know, but I think that taking quantum field theory on its own terms and developing it formally and physically in different directions is at least it might help, right? Again, I think the analogy to classical physics is good here, right? Is that some of the things that were being done by Lagrange, say, were thought of as being pure mathematics that like started out from physical problems, but then didn't really have any practical applications for decades after Lagrange was working in his formalism.
Yeah, for sure, for sure. I guess to get back to the point that I was making earlier about the IR, I think maybe situating in the kind of direction we've taken the conversation the last couple of minutes, I think that the idea was, I think my idea was that even if one takes a point of view a bit unlike yours and says, no, we've got to be good Wilsonians and treat this all as effective, even then it's going to be very hard to give good physical motives for being too literal about the long distance cutoffs. And then once you don't let yourself be too literal about the long distance cutoffs, you're going to have some versions of Hogg's theorem to deal with anyway. And so like even from that kind of approach, that approach doesn't say you get to cut off whatever you want if it makes things convenient. It says you get to introduce cutoffs in situations where the cutoffs are physically well motivated. And that is to say physically well motivated by reasons to suppose that your theory isn't going to cover certain domains in an accurate way. And, you know, you can say that about small distances, but it's much less plausible to say it about large distances. But then once you have the large distance inequivalent representations, then it's already evident that, as you're saying in the essay, right, Hogg's theorem prevents you from applying the free theory concept of particle to the interacting theory.
Yeah, so again, I think there's going to be representational questions about whether, well, there's options you have. You don't need to introduce cutoffs to represent what you don't know about, right? There's different ways of doing that, and I guess this is part of the methodological difference. One thing I wanted to put on the table too is I think it's important not to overemphasize the difference between the distance between the different methodologies. So I was asking earlier if you're thinking about like things merging together. So for example, Kasia Rezhner's work on perturbative AQFT, right? There's, I think one of the things that it's important not to miss, as I said at the beginning, where did the axioms come from? Well, the axioms came from looking at what mainstream QFT was doing. And so it's not like you're talking about starkly different options, right? And similarly, the mathematical advances go back and forth between the mathematical physics community and the mainstream QFT community, right? So I think you don't have to think of it as, okay, there's this fork in the road and you can take one direction or the other. There should be back and forth between. And similarly, I think if you have an eye on quantum gravity, then think about quantum field theory on curved space times, right? And how and there's other problems with particles there, right? So so I think there's ways in which the different approaches can come together and borrow bits and pieces of insight from the other.
Yeah, yeah. Certainly, there are many roads by which you can get to the conclusion that there's no particles in quantum field theory.
Yeah.
So like, yeah, I think that's proving to be a very robust kind of conclusion that a lot of folks have reached, even from different methodological standpoints. So okay, so let's put the free theory to bed and talk about then what goes wrong when we try to take an interacting theory and talk about the vacuum for that theory, talk about what the single particle states look like for that, and then put together a kind of, we might say, like interacting equivalent of a Fock space. You don't consider that to be a good option either. So let's get to that argument.
Okay, good. So yes, so forget about the free Fock representation. We're going to take advantage of the fact that we have unitarily and equivalent representations available to us and try to find one of those that does a better job of giving us a particle representation in the same manner as the Fock space representation does. So there's two ways in which you could go about finding a representation that behaves in the same manner. One way is doing the best you can to follow the physical strategy that you followed in the Fock space representation construction to construct a model for an interacting field. And the second approach is a formal approach. You could look at the formal definitions of your annihilation creation operators, particle state, and you could impose the same formal definitions in the case of for your interacting field. So I argue that neither of those approaches works, right? And the hope is that those are the kind of two obvious things to do, right? So by the physical strategy, I mean the first thing you do is that you Fourier decompose the solutions of the free Klein-Gordon equation, and then you take the positive frequency solutions as giving you the particle states, right? So use those to construct the particle states. So it seems like you either do that or you take the math, you make the formal analogy and you take the math to be the same. If neither of those works out, then the perhaps strong claim I make in this paper is, okay, it's just not clear what you would try next, right? So it's not like, here's a couple of things you might try and none of these things works. It's like, here's all the things that seems to make sense to try at this point if you're going to take the free Fock representation and use it to argue that there's particle interpretation or some sort of analog of the Fock representation for interactions.
Yeah. So just to be clear, the first option is right. It would be take the solutions of the nonlinear interacting equation of motion and try to decompose those into positive and negative frequency.
Yeah.
Right? Yeah. So and that's physically analogous to taking the free states that are solutions to the Klein-Gordon equation and
exactly
doing the usual thing of decomposing those into positive and negative frequency. Okay, cool. Right. And that doesn't work because for an arbitrary solution to the nonlinear field equation, the decomposition into positive and negative frequency states isn't Lorentz invariant, right?
So the first thing doesn't work because you're not gonna have a Lorentz invariant representation. And here's where I have to look at the paper because this is where it gets complicated. And it was like 15 years ago I wrote it. So
I know.
Like,
the trip back in time. I felt the same way when I was looking back at the morning too.
So yeah, the first problem, so I guess I call it the constructive approach. I was calling it the physical approach, but the constructive approach that I talk about in section 4, then you so this is where the one particle states become really important, right? Because the solutions that you get for the free Klein-Gordon equation, of course, give you that the 4-vector k squared equals m squared, and then that's what you need to identify the particle energies, right? As I was making a big deal about how that was important earlier. So so when you try to do the same thing, then you find that the k vector is not time-like, and then you're not going to, you can't, when you promote the fields to operators, then you're not going to have Lorentz covariant fields. So then that is not what you're looking for when you want relativistic fields.
Yeah. Okay. So, okay, good. So there's kind of like, so let me raise another one of these kind of like, is that really so bad kind of concern, right? So like, because the thing that I could imagine, Joe Sixpack, particle physicist, saying, if we kind of come to them with these issues is, well, yeah, like, would you really expect interacting particles to be on the mass shell, right? Like people have this kind of like this thing they say of like, oh, like when you introduce interactions, again, you kind of like end up with like the possibility of virtual particles which are off shell, that is, they don't satisfy the k squared equals m squared relationship. So like, so then um so then I gather your response to that would start from the next thing that you observe, which is, well, if you then use the creation and annihilation operators that you get from this construction to try to make field operators, those aren't going to be relativistically invariant, and like then that's messed up, right? If we don't have, so like so then I suppose the person I'm imagining would have to say, yeah, like, what's so bad about breaking the usual functional relationship between the number operators and the field operators, for example, right? That is to say, like, maybe I could have other field operators that are constructed in a different way than using the creation and annihilation operators to make them.
Okay.
I don't know.
Good.
Yeah.
So so the first thing, like thinking about the virtual particle, like off-shell particles, that's, I think, taking us back to the usual way that comes up in textbooks would be taking us back to option number 1, right? Would be taking us back to
so right. So like now we're imagining doing it without option number 1.
Yeah.
And just saying like, no, we're not so naive as to say that we're going to use the interaction picture and talk about the interacting theory, in as if it were in the free Hilbert space. But we still like the idea maybe that there could be off-shell particles, and like there's nothing against the law about that, right? So maybe that's something that we concluded on the basis of the interaction picture that turned out to be right, and here's the kind of like the mathematically rigorous way of making sense of that or something.
Good. So let me like pose the question like this. If you are only worried about the fact that the masses I was making such a big deal about are not the one particle masses we'd expect from that k squared equals m squared relation, then maybe that's not such a big deal, right? If you just need to adjust the expectation about what the right mass is for a single particle, right? If you have interactions. So I take it that the argument here shows that there's bigger problems than that for these two sorts of proposals. And I think really the underlying problem here is that there just is a really nice harmony between all the ingredients you need in the Klein-Gordon case, right, where you have the free system. And so what's the harmony between? It's between the k squared equals m squared relation. It's the, and then you can also do Fourier analysis, right? And it's also crucial that the plane wave solutions to the Klein-Gordon equation are solutions, and that's what you're doing Fourier decomposing in terms of, right? So when you move to the interacting case, you can see in different ways in the two, like the formal approach or the constructive approach, what's really underlying the problems is that these things don't line up anymore, right? So if you try to make one part of the Fock space style representation work out, if you try to make the physical part work out, then the formal part just gets messed up, right? So then I have a more complicated argument. So I say, like, really now you could promote, if you're going to try to make these quantum fields, then they're not going to be relativistically covariant. So that seems bad. But here's further problems, right? And so the further problems have to do with trying to define your Hilbert space of solutions, and you're going to want your solutions of your interacting equation to line up with the creation operators applied to the vacuum, right? So and that's the thing, doesn't line up either, right? So so it's like you have everything kind of, you have all the elements that lined up so nicely in the free case are now discordant in the interacting case.
And it goes wrong when you take the vacuum and apply the creation operators to it, is like, does it take you out of the Hilbert space, or does it
well, so you have to construct another Hilbert space, and then so this is where so I introduced so I have the A creation and annihilation operators are for the free case. The B annihilation and creation operators are for the interacting case. So the first problem is that you can try, so you're gonna have to figure out how to so you can take the plane wave states and you can map them to the B dagger applied to the vacuum for the different Ks, but then you're not any longer in the space of positive solutions, right? Because that was the first problem, right? Because when you Fourier decompose from the interacting system, you don't get that nice positive negative frequency decomposition. So then you can say, okay, well, like, what if I just take so I have that whole space of solutions. What if I just take the positive frequency ones out of that? Well, then you're going to end up with some sort of integral over different states being what you would get for the single particle state, right? So integral over applying different B dagger operators to the vacuum state. So that seems like then you're no longer formally getting what was so useful in the Fock space representation case. And this is all assuming you just pick like none of this is covariant, right? So this is like, say, like pretending that you can just be happy with picking an inertial reference frame and sticking to it and then doing the rest of the construction in that frame. Right. So that still remains a problem, right? So
yeah, good. Okay, so like so things look bad even if you ignore the fact that you're breaking the laws of relativity. So I guess that's convincingly bad. Okay, so then the next non-traditional option is look for operators that do satisfy the usual functional relationships that we associate with the number operators and the creation and annihilation operators, and like use those ones in some sense, right? That's
but let me I think I'm going to give you something which relates more closely to what you were suggesting, right? So at the end of the previous section, at the end of the previous section, so there's the simple harmonic oscillator analogy. That is the formal analogy that like underwrites thinking about the quanta interpretation in terms of like ladder operators and stuff like that. So I do have some references I noticed at the end of section 4 to Redhead and Huggett
Huggett and
suggesting,
Weingart, right? Yeah.
yeah, Huggett and Weingart suggesting that, you know, if you think in terms of the oscillator analogy, maybe you would not expect independent independent oscillators. So if you think of like interconnected springs, that would be what it would be like. So that might be something that's similar to what you were thinking, right? So when you have interactions, you would expect that it's not like you have the analog would be like a whole bunch of independent simple harmonic oscillators. It's that you would have like they would somehow be connected, and then that would be an effect of the interaction.
So a thing that's in the background here, right, is this picture of like a way of understanding the quanta picture of particles in free quantum field theory is like you can think of the free states as analogous to kind of like collections of harmonic oscillators, and the particle states are like modes of the oscillators, right? Like,
Yeah.
yeah. Yeah. Um, good. Yeah.
So that's, I mean, so that's a kind of that's suggestive of a different way of going, but it's not clear what you do with that, right? So as
Yeah.
you say, it's like that's like gives you a kind of intuitive picture, which we don't think corresponds to the way the actual world works. So I would call that kind of thing a formal analogy.
Right.
So that could give you an idea about potentially about how to set up the uh, how to set up the uh, representation differently. My reading of it was, I think the suggestions in mathematical terms that you need to do something other than Fourier decompose, right? Because it was the plane wave solutions that were the solutions of the Klein-Gordon equation. They're not in the interacting case. So Fourier decompose in terms of something else, but then it's I guess, a highly non-trivial mathematical problem to figure out what the other functions would be that you would decompose into that would make, you know, give you a complete basis, and you want a complete
Yeah.
basis for your Hilbert space. And so like, I think that's uh, like maybe suggestive, but it's not clear how you would actually go about
Yeah.
implementing that as a practical strategy.
Yeah. Yeah. And you might be pessimistic that kind of as you so you point out that like um the usual nice that is nice, like physically meaningful seeming relationships between different quantities that we had in the free theory, um, they break down when you um, try to do this non-relativistically invariant trick of uh, frequency splitting for the interacting theory. And you might think this is good grounds to worry that those functional relationships aren't going to be restored, even if you could find some invariant way of doing something that's kind of analogous to frequency splitting or something.
Right. Because you'd still have to wind up with something that was um, relativistic and gave you a complete basis, right? So those are the two kinds of
Yeah.
requirements that are going to be minimal for constructing your Hilbert space.
Yeah. Cool. Okay. So now let's talk about the um the option of looking directly for candidate number operators and creation and annihilation operators, right?
Yeah.
So what goes wrong with
So,
that?
okay, good. So the physical construction strategy doesn't give you annihilation and creation operators. So then you can say, okay, well, we know we want annihilation and creation operators. So let's just formally impose that condition and then try to work with that. So then what goes wrong in that case is that you are going to well, the vacuum state is going to be the vacuum state for the free field once again. So then you're back into the problems that we had in the first case, right? So uh, so in order for it to be no particle state, it would have to be in order for the no particle state to be the vacuum state, you would have to have a free field, and we don't. So that's a kind of like a corollary of Hogg's theorem is related to like conditions under which you have unitarily inequivalent representations. And then the other problem is that when you look at what the formal creation operators give you when you apply them to the no particle state, then those are supposed to be the one particle states. And so if you could just I just took a simple example of, again, the scalar 5-4 case. And so when you apply, when you ask what the energy is, if you apply that Hamiltonian to the state, then you don't get the right energy from the relativistic mass energy relation. And then this gets back to the question, okay, so if that's not how we identify what the single particle states are, then how else are we going to know whether we're counting particles or any, what else, what are we counting? Is it particles or something else?
Yeah, good. So this, I feel like, is where that idea of nulls comes in, right? So as I understand the idea that he had a while back, it would be something like what's wrong with dropping the assumption that single particle or zero particle states are physically possible? Maybe we have a theory where the laws only allow states that have infinitely many particles. And that's kind of odd, but you could think of it as kind of physically motivated in the sense that, like, for example, in QED, we say, like, well, the electron is always followed around by a photon cloud, and if those photons are allowed to be like arbitrarily soft or something, then maybe it would make sense that kind of like there wouldn't be finitely many of them in a certain, so yeah, you might think that there's reasons to think, oh yeah, and this is all speculative in the sense that clearly nobody has kind of gone through and done the work of saying, like, well, how do you make sense of an approach like this? But the thought might go, well, there's a speculative way out from the argument, which is to say, interacting theories are theories where all the possible states have infinitely many particles, and the physical differences between the states aren't differences about how many particles are there total, but rather, like, how do we talk about the other physically contingent properties of those particles?
Yeah. So actually this might take us to the conclusion, right? Because the whole setup here was supposed to be, the set them up and knock them down kind of setup, right? So argument by elimination. So I've eliminated what I took to be the three plausible options. And then I've tried to argue that, okay, if you don't do one of those three things, it's not clear how you're going to proceed with this project of interpreting interacting systems as containing particles in an analogous way to how you do it in the free case. So that leaves open the response, though, that, look, you forgot an option, right? So I think there's a couple different ways maybe you could go with that idea that every state has an infinite number of particles or something like that, right? One thing you could try is you could try to maybe use some ingredients of the Fox-based representation. Then I don't know, that might turn out to be a continuation of probably, you're right, probably the second option, where you like take the skeleton version of or the formal definition of the creation and annihilation operators, and then you have the vacuum. But I think once you've gotten to that point, there's no reason. I think you're so far from doing what we do in the free case that you can like you can look at other ways of setting up your representation and then argue that there's other ways of interpreting them in terms of particles. So I think, yes, it's true. I haven't ruled out any other options. I guess the challenge is to figure out how exactly you would both formally set up a representation for interacting systems and then physically interpret it in a way that would give you even minimal grounds to think that it's representing particles.
Yeah. And one of the things, I mean, like, to get back to something we were talking about before, I think one of the things that would be at least kind of like a big concern about this approach is like, well, you want something where the free theory can be a good approximation to it, a domain where the interactions are super duper weak. And it might be kind of hard to say, well, like, how do you do that with a theory that's so qualitatively different from the free theory, that like it has just for example, like a completely different relationship between particle number and total energy compared with the free theory or something like that, right? You might think like the prospects for coming up with a theory that kind of limits to the free theory, or that is well approximated by the free theory in the kind of like weak coupling domain,
right?
The prospects for that are no good.
Yeah. And then actually the next section talks about scattering, right? So
yeah.
So that would be one context in which, as you say, like in the limit in which coupling goes to zero, or interactions go to zero, then you want to, in some sense, in some respects, recover the free Fock representation.
Yeah.
I think actually maybe the bigger question though is like, why, right? Because this is, as we started at the beginning by talking about how this is like one of a number of different arguments that you don't have particles in your fundamental ontology when you're asking the question about what QFT represents. I mean, and that's a question, and that's an answer which you get whether you take my kind of attitude towards interpreting quantum field theory as describing a possible world that's maybe not our world, or else you take a more liberal approach of trying to use quantum field theory to tell us something about our world, right? So in that case too, you might recover descriptions in terms of particles, but they're not going to be fundamental particle descriptions in any, you've given up on that, right? So then I guess like, I mean, I guess it's always good to figure out whether there's options we're missing, right? And what the interpretive possibilities are. But there just seem to be a lot of problems with thinking about particles as, or being what quantum field theories describe in any kind of fundamental way. So
yeah, good. So this does kind of move us into the domain of your newer review article, because a lot of what you do in that paper is talk about, well, what can be saved about particle ways of thinking. There has to be something right about them, or else it wouldn't be so natural for the folks at the LHC to talk about particles when they describe the stuff that they measure. So like, what's the sense in which those, in which particle talk is correct? And you kind of go through a few options. So as I take it, the options are, you could be an operationalist and say, well, what's going on is just that we have data that kind of looks like there are particles, and that's all that we kind of mean when we talk about particles, is that like that the measurable data is very close to what a theory of particles would predict, or that it's kind of like uh, the measurable data can be usefully thought of in a kind of particle way. You talk about approximation pictures on which it's literally false to say that there are particles, but in certain ways you get close to the truth by applying a particle description to the state. And then you talk about emergence views where which are kind of closely related, I thought, to the approximation views, really. But you go the further step of saying, because theories with particle observables are a good approximation to the real truth about interacting field theory in certain domains, that means that it's literally correct to say that there are particles, just the particles aren't fundamental, right? They're kind of like
effective or emergent or whatever.
Yeah. I mean, so one of the things I was wondering about this part of the paper was, it's a review article, so you're not taking a strong position yourself. Do you have a preference between these three options? Like, which of them kind of seems best to you?
So that's a good question. You didn't put actually. So the one I actually talked about more in terms of my own work was the anti-realist option.
Oh, right. Yeah.
At
Yeah.
the
Then
end of the paper.
you could just be a nihilist. I mean, right. Right. Yeah, you could just say no particles, period.
And that's more of a kind of like view, like, I mean, but we're talking about this simple harmonic oscillator idea, right? You can think along this, so that's a kind of intuitive picture you can have that goes along with the mathematics, but we don't really think of it as attaching in any way to what happens in the world, even in an approximate way, right? It's just an intuitive picture that fits the
That's
math.
what you
But
call the kind of idealization option. Is that right? Like, it's like you have states that are kind of fictions that you use for certain purposes, but you understand that like they don't have a very direct relationship with the reality or something. They only have a kind of resemblance relationship with the reality.
so there, I think the anti-realist view is supposed to be more extreme in that not even having
Oh,
a
okay.
resemblance relation.
Yeah.
Which is why I think one of the interesting things happening in the background that I've been thinking about more recently is that field theories, quantum field theories, get used to represent all kinds of different systems, right? So the issues in the Fate of Particles paper have to do with specifically relativistic systems, but there's certain applied mathematical or modeling strategies that come up in condensed matter physics, that come up in relativistic quantum field theory. And so that's what the last section is about, is thinking about that, right? And so then I think this is more of gets you into thinking of representation in more of an applied math mode, which doesn't, which can lead to this kind of point of view that, there can be useful pictures to go along with the mathematics that you're using, but they don't necessarily need to be, or shouldn't necessarily be read in a straightforwardly representational way, right?
Yeah. Okay. Pretty hardcore.
In terms of
Well, in terms of, I mean, like one thing that's hardcore about it is like does it involve a fairly strong error theory about what people are saying at the LHC?
oh uh I was thinking of it more in terms of um well, I think I don't know. I guess that's like so which of these options doesn't involve a fairly strong error theory, I guess, right? Like
Yeah, I mean, I guess like so it feels to me like the emergence one is one where you could talk to somebody at the LHC and say, "Oh yeah. There's real protons. They're just like um
scale relative or something like that,
yeah,
right?
they're
Or
scale
like
relative and if we talk about things at too fine a grain, we'd have to realize that it's not literally true that they're part of the basic furniture of the universe, but they're part of the non-basic furniture of the universe. They're as real as like, like you might say they're as real as like tables and chairs are, just tables and chairs are made up out of other stuff that isn't tables and chairs, and protons are kind of like made up out of other stuff that isn't protons, right? And isn't
Yeah.
quarks either on this picture.
Yeah, right. So they're patterns in something, right? So
Yeah.
they're real patterns. Yeah, I mean, I would push on like um uh there's a sort of structural realism. So I think there's a kind of particular kind of structural realism that underpins that view that I don't find persuasive.
Yeah, I hate the real pattern stuff. Don't get me wrong. Like, no offense to the real patterns guys, but like, yeah, it's just like it falls flat for me too.
Yeah. So maybe one of the so I mean, I think um it's maybe uh so you can be a structural realist or structural anti-realist. Maybe that's the difference between the emergence option and the and the anti-realist option, right?
Mm.
And I think the real question there, and here I'm thinking about some of Laura Ritchie's work as well, more recent work, is in thinking about what exactly the claim amounts to that you're adding in interpretation to the
Yeah, yeah.
formalism, right? And so what I really play up in the last section, this is the thing that I've been interested in more recently, is these you do find formal similarities, like so quasi-particles or formally like particles, but the question is, does that license you to believe in both as entities in the world, quasi-particles and particles, or is that a useful representational strategy that applies very generally when you have a lot of degrees of freedom, and then like stick in a bunch of other effective field theory kinds of assumptions that need to hold in order to have that kind of picture being useful, right? So
Yeah, yeah. I mean, so I know that Laura has kind of moved in a very anti-realist direction, not just about particles, but kind of like period, right? Like she's kind of, it seems to me like her current views are, it makes the most sense to be a scientific anti-realist if you're looking at questions about quantum field theory. Like these kind of things should make you pessimistic about whether we're getting at really real stuff in the first place. Is that like, are you gripped by that, or is it
so I think
specific to
that's
particles?
similar in conclusion. I think the arguments she gives are different than the ones I'm giving here,
Yeah, yeah.
are more just thinking about the role that mathematical representations play. And as you get further and further forward in physics, right? So let me maybe put it in a different way. So one project I could have engaged in after I wrote this paper saying that there's no such thing as particles is I could have asked the positive question, right? Of like, okay, so what it really is it that our quantum field theories are representing? And I think that's a really interesting, important question. And it's a question I've never really gotten around to thinking about. This is a kind of different question, which is that is thinking more about the applied math aspect of what's going on in particle representations, where really what you need to make these kinds of representational strategies work is very thin in terms of physical content, right? So I think that's more of the direction I've been thinking of. And so I should say I haven't been thinking so much about particles in that context as like renormalization group methods and spontaneous symmetry breaking and other types of what I would classify as, broadly speaking, representational strategies that get used across condensed matter physics and relativistic quantum field theory. And I think there's interesting historical, like the history of how these strategies get passed back and forth between the two fields is also kind of interesting. So,
Yeah, 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 Yeah. I mean, to return to the question of how revisionary the options are, I guess like I'm also a little bit inclined to say that just the approximation option is not that revisionary.
Mm.
Like if you kind of went to somebody at the LHC and said, well, it's only approximately true that there are protons. And if you kind of like look at things at small enough scales, it becomes a bad approximation to the truth to say that there are protons. But if you look at bigger scales, then it becomes a good approximation to the truth to say that there are protons. But literally speaking, there aren't protons. It's all
So
quantum fields,
maybe
whatever
it's
those are.
maybe it's worth underscoring here that the sense in which you approximately have particles in that approximation view is the sense in which you have approximately localized descriptions, right? So, so this is going back more to the Malamud strain of arguments against particle interpretations of quantum field theory. So then the sense in which it would be approximately true is, oh, yes, the representations are representing something that's approximately localized, but not actually localized. And that sounds like a field to me, right? Like, so, um, so I think if you put it in those terms, then I think, sure, I mean, in some sense, it's approximately true that you have something that's approximately localized, but it's not necessarily approximately true that you have something that's a particle.
Yeah, that's interesting. Um, and because you're thinking that there are further criteria that need to be applied before you can say it's a good approximation to the truth that there's a particle beyond it's a good approximation to the truth. There's something that's kind of like localized and acts like it has.
And so then this gets more into the question about like what exactly are we going to demand
Yeah,
of the properties of the things that are described by quantum field theory, so that such that they count as being particles and not some other kind of entity, right?
right.
But I think that kind of approximation move is focused on the localizability property, right? So
Right. That's what Halverson and Clifton go
yeah,
into. Right. Yeah, I mean, yeah, right. I mean, I guess maybe it's kind of like less well explored, but but probably you could say a similar thing though, like in the sense that like, you know, so like so the folks that talk about scattering, right, they
mm.
could say, well, there is this domain far away from where the interaction happens, um that limits to the free states. And then you can see how there's kind of like they can say, well, that's kind of the domain in which it's a good approximation to say that the states have the properties that we took to be particle like about Fock space. And so, you know, um not only is it a good approximation to say that there's localization, but it's a good approximation to say that there's other particle properties that we were treating as kind of like necessary conditions for there being particles or something.
Yeah, because the approximation issue, yeah. So you'd have to like if you really wanted to. I mean, I think what we need to recover is the particle talk, right? So
Yeah.
maybe I'm more minimalist about what we need to recover. I'm not so bothered by whether there's philosophically um compelling sense in which you have like entities that are emergent or approximate or idealizations or anything like that. But
Yeah. Can I say a bit about why it matters to me, I guess?
Yes, please
I,
do.
yeah, I mean, I guess I kind of feel like well, this gets to whether we should be as anti-realist as Laura Ritchie tends to be these days, right? It's like I guess I kind of feel like it would be nice to have a picture where even before quantum field theory, when we were talking about the atomic hypothesis being true, which is kind of one of the things that you kind of get into in your paper, right? In your review article, like that we were kind of getting close to the truth when we drew that conclusion. And not just in a kind of we were getting close to the stuff that you need in order to operationally predict experiments, but we were getting close to something about the way that reality is, right? So that would make it nice to be able to say, um, you get close to the truth by talking about particles in certain ways.
Yeah, I think, yeah. Uh, that case, though, I think, are you gonna, and maybe this is going too far from the topic here, but like something to think about is you can also help yourself to not just approximation regimes in which you have negligible interactions and um, things are approximately localized, but you can go all the way back to non-relativistic quantum mechanics, right? If you want to go back to the atomic hypothesis initially. So like if you can help yourself to that limit as well, right? Then you're
I think you probably should be able to if this is legitimate, right?
yeah,
If this
yeah.
is kind of a legitimate way to talk. Yeah, yeah.
um anyway, I wanted to say one other thing about that review article that I've been thinking about in a completely different vein more recently, which was the operationalization idea, right? So one of the things I've been thinking about more recently is detector models. I've been thinking about measurement in quantum field theory more recently. So this has led me to look a lot more into uh, what I think would be loosely under that. Well, yeah, definitely be under the operationalism option, which is more sophisticated types of detector models. So you might think of the detector at the LHC, but actually, like if you are interested in information theoretic tasks, there's a group I've been collaborating with at Waterloo that is interested in relativistic quantum information. So that's a context in which you want to use quantum field theory to represent relativistic systems. And of course, it makes sense if you're interested in information theoretic constraints, actually, you should take relativity into account in a serious kind of way. But then this poses interesting questions about it makes it more of a practical question whether there's particles or not, right? In a way. So one of the ways in which the tasks, the local tasks they're interested in get set up is in some sense, usually about information transfer through the field. But then you also have these detectors, and then the detector models get more and more sophisticated. So you start with like Unruh DeWitt type detector models where you have like a two-level system or something like that that you've coupled to your relativistic field. But then there's all sorts of things you can do from that starting point to make it more sophisticated, that look at different parameter regimes and different systems and things like that. So I just thought it was interesting to mention that that's one area in which I think questions which have been looked at by philosophers are actually starting to come into to be actually practically important in the physics that's happening right now.
Yeah. Well, and you've started to work on measurement in quantum field theory. I take it this is kind of uh part of what's behind that project, right? So
Yeah, so that's one of the, I mean, there's a bunch of different, again, you get the same thing coming up when you think about measurement that we talked
yeah,
about much earlier in this discussion, right? Where there's not just one way of setting up measurement,
yeah.
local measurements. Uh, so there's different approaches to doing it.
I mean, speaking of the measurement problem, maybe we should talk a little bit about, well,
Oh dear.
so a thing
Makes
that
me nervous when people say speaking of the
well,
measurement
I
problem.
mean, a thing that I've struggled with over the years, right, is like, how do we um how do we connect the kind of stuff that you and I sometimes like to do about quantum field theory with like so so we're so these kind of papers, like your paper, and I like I said, right, I'm kind of lumping myself in here because I've written a lot of papers that have similar kinds of approaches. So um like what are we doing? Like so what we're kind of doing is we're looking at physical conclusions you can draw about quantum states understood as being kind of like complete in some sense, right? Or like we're kind of pretending for the purposes of this work that the the kind of ordinary, I mean not ordinary because it's like we use lots of different uh like algebraic methods and stuff that aren't used that often in practice, but that the yeah, like the ordinary quantum description of the state is kind of all there is to what the state is talking about, right? And I mean that assumption kind of like if we're really assuming that, you might think, for example, that well, the work might be straightforward if you think of it as existing within the many worlds interpretation where um the state doesn't need to be changed, but it's like like what are we doing if we think of it in terms of other possible ways to interpret quantum mechanics or quantum theory or something, right? It's yeah, I don't know, it's just something I've always kind of like felt like, oh, like how worried should I be about the fact that we're ignoring that problem?
I, I mean, so this is the problem of what the measurement problem looks like in quantum field theory.
Well, and the problem of like so for example, right, so let me draw a kind of concrete connection between the thing that I'm saying um and the fate of particles paper,
Okay.
right? So as we were kind of discussing, right, the structure of your no-go arguments is um well, if you want to say that there are particles, you're going to have to say no to certain plausible assumptions, right? Like you're going to have to adopt a view that's strange in some respect, or that says no to some of the following kind of commitments that we're kind of assuming we have going into the discussion, right? And that do look good for various reasons. I mean, I can tell you, like so you might think like, where would a Bohmian get off of the boat, for example? Like where would somebody who likes Bohmian interpretations of relativistic quantum theory, where would they say no to those assumptions? Because of course they believe that they're particles, right? Well, the assumption that they would say no to is the assumption that the particle degrees of freedom are described by observables
Mhm.
in the quantum theory, and they would say no, like the particles in quantum field theory understood our way aren't observables. They are like that is when I say observables, like I mean technically kind of a particular kind of operator on the um on the space of states, right? They would say no, that's not the right way to understand what particles are. Particles are another kind of variable. So so it's like in other words, like it's like um with with that point in mind, it's kind of I guess it kind of illustrates like how difficult it is to avoid taking on commitments that on some level align you with a faction in the debate about the measurement problem, because it's like you know
Ah,
yeah, you
I
like one of the things and again, like I do this too, right? One of the things that you're doing in the paper is on some level saying no to the Bohmian approach.
Yeah, although you might say that the Bohmian approach would come out at the end, right? So I start out by talking about Fox-based representations and about how I start with quantum field theory. I don't start with non-relativistic quantum mechanics, right? But within quantum field theory, that seems to be the way to get a particle interpretation off the ground, right? So I think then I show that approach doesn't work out. I think the Bohmian would have an additional burden, which would be to go all the way back to non-relativistic quantum mechanics, Bohmian interpretation of that, then come up with a formal proposal for quantum field theory that satisfies the Bohmian interpretive constraints. And then that would be like a response, right? So at the end of the paper, I say, okay, like if you're going to develop a particle interpretation from quantum field theory another way, that's like a program that like you need to, it's not clear to me how you're going to do it. That would be a template for doing it, but then it would still be a program that would need to be completed in a satisfactory way, which I take it the Bohmians are still working on that, right?
Yeah,
so,
yeah, for sure. Yeah.
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 But the deeper point, I guess, is maybe a sense of unease about the disconnect between foundational interpretive debates in quantum field theory that are situated within quantum field theory and the ones that we've known for much longer in quantum mechanics, right? And how do you make these two kinds of debates come into more contact with each other? So
I mean, maybe they don't need to, but like, you might think that they should, given that there's probably some shared subject matter or some subject matter that we should think of as shared, right?
Yeah. I mean, I should say, I think one of the motivations I've had for thinking more about local measurement in quantum field theory, we've been talking a lot about scattering types of scenarios where you have measurements like at the LHC, say, which we represent using asymptotic in and out states. And then the question is for if you're interested in information theoretic tasks, then it's often really important that you are modeling operations that you do that are local, right? Local in space time. So then the question is, how do you do that? How do you represent measurement in that context? That's one of the reasons why I'm interested in those developments. Is I'm less interested in the practical implications like as a person, I'm interested, but from my own research perspective, I'm interested because I think this is a place where there's going to be more contact with the traditional measurement problem from non-relativistic quantum mechanics. And so that's, I don't have much to say about that right at this moment, but that's one of the reasons why I think there has been a disconnect between if you think of traditional work and foundations of non-relativistic quantum mechanics, the measurement problem is a big problem. Not to say that it gets solved automatically when you move to quantum field theory, but I think there's questions about what exactly the problem looks like in terms of local. And one of the reasons is because like how you represent local measurements has been a question.
Yeah. 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 So maybe the answer is that like in a year or two, you will have something to say.
You can interview me again.
Brings the two together.
Like...
Yeah.
Yeah. But I think I do really, I mean, I think one way this debate can be unproductive is like people worry that if you do foundations of quantum field theory, you think the measurement problem is not important, or you think it's somehow automatically solved in quantum field theory. And I don't believe that at all, right? But I do think...
I don't think anybody thinks that.
Yeah, no, and nobody should think that, right? But I do think that there's and just in the past couple of years, there's been more papers on questions about like maybe I'm thinking here particularly of David Wallace, but also papers responding to David Wallace about what the fate of interpretations of non-relativistic quantum mechanics is in relativistic context, in the context of quantum field theory. So
yeah, and I mean, maybe Wallace is right, and the right conclusion to draw is just that, the many worlds theory is the only game in town when it comes to relativistic field theories. And then, I mean, if that's the case, then there's nothing wrong with doing philosophy of quantum field theory in a way that sort of ignores the measurement problem, right? Because it's like many worlds solves it. I mean,
I'm not going to agree with that conclusion, but
well, it's an interesting, it
so,
makes for an interesting conditional conclusion, right? It's like,
yeah. So I think the thing that's more interesting to me is it's not clear to me why the measurement problem has to be the same in quantum field theory as it was in non-relativistic quantum mechanics. I mean, there's all sorts of elements of the way you set up the measurement problem that make non-relativistic assumptions. Right? So
yeah.
So and that's not to say that the measurement problem goes away, but I think once you have the problem takes a different form, a relativistic form, then it's not unreasonable to think that there's going to be different interpretive options too, or different possibilities to solve it. So even if you think David is right, that if you focus on non-relativistic quantum mechanics, the only interpretation that survives to QFT is the many worlds interpretation, that doesn't mean that there aren't more interpretive options for QFT, which is, I think, one of the really compelling reasons to study QFT on its own, right? To take QFT seriously as its own kind of a theory as well, is that can open up new interpretive options that weren't available in non-relativistic quantum mechanics.
Yeah, it's an exciting prospect. Well, this has been awesome. Is there anything that you feel like you wanted to get to that we haven't gotten to?
No, I think we've gotten to an awful lot.
Yeah, I feel like this has been wide ranging
thanks
and
for
really
fun,
cool.
Dave. It's yeah.
Yeah. Well, hey.
Thank you for making me reread that paper, and
thanks for doing it. I mean, it's like, as I was saying, right, it's a paper that has had a big impact on my thinking over the years. And like,
actually, I do have one question for you, which
yeah.
is like, so your paper, right, which then extends the argument to the argument against fields, whether you've thought any more about that, or
I mean, I have. I think, like, honestly, I was saying to a friend a while ago that, that's probably the paper that's going to adorn my headstone someday. But it's kind of the one that I've written that I like agree with the least in the present. Like, I feel like there are some assumptions that I was making that I don't 100% buy into anymore. I get into this a bit I wrote a review article about philosophy of quantum field theory around the time I got tenure. So like, and I think it came out 2016 or something. My Oxford handbook article, and yeah, I kind of feel like I was making some somewhat naive assumptions about the connection between observable operators and physical quantities. In that paper, although that doesn't apply to the part of it that's about interactions, right?
Yeah.
But a thing that Chip Siebens, has kind of has jumped on about that paper is, when I talk about the unitary, so one of the things that underlies the idea for the paper, although I don't think it's actually that crucial to some of the main arguments, but like one of the things that's kind of like spiritually going on in the paper is the observation that that wave functional space, or the space of superpositions of field configurations, is unitarily equivalent to Fock space, right? Now that's true if you define wave functional space as the Hilbert space that you get that's made up out of normalizable wave functions, or normalizable fields. But if you allow your classical fields to like to not go to zero at infinity, then nobody has done a rigorous construction of that wave functional space, but it would be a different one. So I mean, what I took myself to be doing at the time was saying, well, this is the one that you can rigorously construct, and so it's the one that you gotta work with. But I feel less happy with that move in retrospect.
Right. I read that move as being analogous to my move of saying, okay, you could renormalize that free flock representation.
Yeah. Yeah, I think there
But
is
then, yeah,
and as you as came out in this discussion, right? I think I'm a little less comfortable with that kind of move than you are.
right.
So that's kind of where I'm at these days. I think in general, right, I kind of like um I was more in a place then of thinking just work within the axiomatic approach, and conclusions you draw doing that are going to be good.
Mhm.
I'm less confident about that than I used to be. But that's not the main. I mean, like the main thing, like I was saying, the main thing that I would now question about the um the best arguments in that paper would be the way that I assume a pretty tight connection between mathematical observables and field quantities,
Right.
um, which like yeah, I guess I would for anybody who's like, what the hell is he talking about? I guess just, yeah, look at the review article, and I kind of
Yeah.
go into the way that I get off the boat of some of the things that I said back then. But yeah, I mean, like, um, I still like the paper in the sense that I think it's like one of my most well-written papers, and like it's kind of it's I think it's a really great paper to learn from. But do I now agree with the argument? Not that much, actually.
That's good. I think it's important for people to change their minds about things as
I think so too. Like, I don't know. I feel like that's one of the biggest things that a way that I've changed my mind is that I've come to realize how important it is to change your mind. Um, all right. Well, such a delight and such a trip down a wonderful memory lane. Uh,
Yes.
with looking at like I said, right, one of the classics of um, the quantum field theoretic age of philosophy of physics, which we're still in. Other things are kind of rising up as well, but this is still important work, and I don't think anything has been written since that supersedes it or does anywhere near as good a job of kind of getting at the questions that you're getting at. So it was great to get back to it.
Thanks, Dave. Nice to talk to you.
All right. Well, I'll wish you and our listeners goodbye then.